Hi everyone. The next thing we want to work on, oh, this says arc length intro. Yep, is arc length. I was just going to talk myself out of it, but that's exactly what we want to work on. So we're just going to kind of break this down the way we broke down the different angles by knowing what's going on when you have the entire circle and then breaking that into smaller pieces and seeing if we can spot the pattern. So we're going to start with a circle with radius 3. So we've got this guy right here is 3 inches. And we're going to start with the question, if we rotate all the way around the whole circle, 2 pi radians, how far does this point P at the end travel around? So we want to know if you're traveling around the outside of a circle, can we figure out how far you've gone distance-wise if we know what rotation we have to travel through to capture your distance? And this again goes back to just the circumference of a circle, right? So this is really just saying, okay, what is the circumference of your circle? And we know that's 2 pi times the radius. So our circle has a radius of 6 pi inches, and that's the answer to the question. If you rotate through the entire circle, that point on the end of the segment will travel 6 pi inches. So then we can break it down a little and say, okay, well, what if it only travels through pi radians, which is halfway around the circle? And really, I would just think about that and say, okay, well, if the entire circle has arc length 6 pi inches, then half the circle will be half of 6 pi inches, which is 3 pi inches. And then we could go to pi over 4 radians, which we could do that as a fraction of the last one, but I'm going to go all the way back to the beginning again because that's how we get our formula and say, okay, well, pi over 4 radians, that's actually an eighth of a circle. So this was half of a circle. This is an eighth of the circle. So if we take an eighth of 6 pi inches, we get 6 pi over 8, which is 3 pi over 4 inches. And this is kind of our strategy. If we can just figure out what fraction of a full rotation we've done, then we can use that to fraction of the circumference of the circle to get arc length. And really what we're doing there is we're solving a proportion. We're saying, okay, I'm going to use S for arc length. That's kind of traditional. So if S is our arc length, the fraction of our entire circumference, so our arc length over our entire circumference should equal our angle over an entire rotation. And this we can solve for S really easily. We're just going to multiply both sides by 2 pi r. And it even reduces quite a bit. The 2 pi actually cancels out of that. So we just get S equals theta times r, which traditionally we write it r times theta. So I'm going to go ahead and switch order on that. And that's our arc length formula. So we've got it down here. S equals r theta is the formula for the arc length on the outside of a circle. But truly, if you ever space out on that, it's not a terribly complicated formula, but people will forget about it. You can just go back to this fraction of a circle thing, even if it's an ugly fraction. If you figure out that you've got, I don't know, 5 pi over 12 radians in there, figure out what part of an entire circle rotation that is, and then use that fraction of your entire circumference to get the arc length. I do have a quick demo. I think it's probably more for you to play with than needing to see me play with it, but I'll bring it up real quick. So this one is just so that you can mess around and you can actually change your angle. Let's shrink this down just a little bit. And you can change the, radius of your circle just by dragging that, and it lists, I didn't get it to do it on the picture, but it lists over here on the left hand side your arc length. So you can see that my arc length right now is about 8.5. If I increase the angle, that's going to increase to a little more than 16. I can also, let me put it back over here, increase the radius, and that will make the arc length bigger. Now it's about 8.7. I can shrink the radius down. It makes it smaller. So nothing too crazy here, but if you want to play around a little bit just to get your intuition to match with what's happening, that is available for you. It also looks like I got into all the Greek alphabet letters here, but I did that in a video in a later section. So if you'd like, there's a link here to a whole list of all the Greek alphabet letters. But basically just expect to be seeing a few of these. I guess one that I didn't talk about is omega. We're going to use that soon. That gets used a lot for angular velocity, a little omega. So expect to see those. Otherwise, for this section, S equals R theta, really important. And I want to really stress that theta has to be in radians for this to work. We base that on 2 pi radians in a rotation. Otherwise, you could go back to the beginning and try and set up a proportion. You could say S over 360 is equal to, S over 2 pi r is equal to theta over 360, and you could solve that way, but it is a little different, and my advice is just use S equals r theta. That's super easy to remember compared to what we did up above, and just make sure you always do a conversion from degrees to radians if your angle is in degrees. Okay, I think that's it for now. Thanks for watching.